It's like this. Air pressure is always pushing on us from all sides. About 15 pounds of pressure for every square inch. But at the same time, our bodies push back against the air pressure with equal force. So it balances out and we don't get crushed.
I wish I could see all this.
Well, think of it this way. Picture air molecules near the ground as being packed tightly together by the weight of the air above. This is why air is much denser at sea level. But higher up in the atmosphere, there's a lot less air pushing down from above, so the air molecules are not packed together so tightly. Normally, we don't feel any of this unless the pressure changes suddenly.
You mean like when your ears pop in an airplane?
Exactly. At much greater heights, there is less air weight pressing on you. Your body is reacting to the pressure change.
Scientists use barometers and other tools to study the air pressure, to predict the weather, and to study climates.
This kite surfer is hitching a ride on a moving air mass. Our transparent atmosphere reveals itself when it starts to move. Moving air, of course, is wind. The atmosphere surrounding us is a deep ocean of air extending for kilometers above us. We know that the atmosphere is essential to life on Earth. The components of air, particularly oxygen and carbon dioxide, play a critical role in the chemistry of life. Another important aspect of air is atmospheric pressure. We live at the bottom of an ocean of air. Gravity pulls on this massive layer of gas, creating pressure. The pressure is greatest at the bottom, the Earth's surface, the level where we live. Pressure is a force per unit area. The standard SI unit of pressure is the Pascal. 1 Pascal is 1 Newton of force per square meter. You will also find PSI, or pounds per square inch, used in parts of the world, particularly America. Air pressure at sea level is 14.7 psi, or 101.3 kilopascals. That's over 101,000 newtons of force per square meter. If you have a small kitchen table, 1 meter square, the force on that area created by air pressure is approximately 101,000 newtons, equivalent to the weight of 10 cars sitting on the tabletop. If air pressure can generate such huge forces, why don't we notice it? Why doesn't the table collapse? It turns out that pressure in a fluid like air transmits in all directions, not just down. This means that the 101,000 newtons of force pushing down on the tabletop is balanced by 101,000 newtons pushing up. Forces are balanced. Similarly, our bodies are not crushed because the fluids contained within our skin exert a pressure that balances atmospheric pressure. Here is a simple demonstration that reveals the presence of atmospheric pressure. Fill a glass with water. Cut a small piece of card large enough to cover the top of the glass. Lay the card on the glass. Hold the card in place and rotate the glass full of water. Surprisingly, the water stays in the glass. Here's the explanation. The card provides a rigid membrane between the water and the air in the room. Air pressure pushes up on the card. Air pressure is not pushing down on the water because there is a vacuum at the top of the water. Air pressure is pushing on the outside of the glass, but this does not affect the water. The only downward force from the water is its weight. The upward force of air pressure easily supports the weight of the water. If we drilled a hole in the top of the glass, air pressure would push on the top of the water would fall from the glass. The forces involved in our